Hello everyone, my name is Sercan. I will be presenting today the Unary is all you need by using the Unary computing in the hyperdimensional computing. This is a collaborative work between the University of Louisiana and Case Western Reserve University. In the umbrella term of emergent computing, this work targets synergize between two computing paradigms. One is Unary bitstream computing and the other is hyperdimensional computing, abbreviated as HDC. Our proposal will be targeting end-to-end bitstream processing from input to output in the hyperdimensional computing setting, HDC. We will be migrating from random process and we will be using the deterministic computing such as Unary bitstream processing. Let's first see the background in HDC for training and inference setting. First, we need to define what is the atomic data in HDC. It is hypervector containing plus and minus ones in this slide setting and also the simulations. But in real hardware, the plus one represent the logic 1, minus 1 represent the logic 0. Anything, scalar value or symbol can be represented in these hypervectors. In the training, we have, let's say, a three type of class, 0, 1, 2 from MNIST. And for this one, we first need to combine all those pixels, their positions together for each specific sample, such as 0, which will be contributing to the 0 class by an encoding mechanism. Then I generate hypervector for any specific input. Then for training purpose, I need to contribute to the corresponding class. For instance, assume my incoming input is 0 class. I need to contribute to the class hypervector, which represent the 0 class. So in my training data, all 0 class images should contribute to a class hypervector. And I will at the end have, for this specific example, 3 class vectors representing 0, 1, and 2. This class hypervector make my associative memory, and at the same time, when I use this already learned model, my inference, which is called item memory, will be encoded in the same way. Let's assume I have a testing data from class 1. I use the same encoding steps, including the generation, and I have a query hypervector, which is shown in here in lowercase h in red color. But the classification will only require a simple similarity calculation. My already calculated class vectors will be one by one compared with this existing query hypervector, and the simple similarity score will just show which class is the most similar, will be decision of the class and classification. Overall, we have an encoding as an important step. And this starts with hypervector generation, which we will see in a couple of slides. And our proposal will be based on these different generations using deterministic approach and Unary computing. After we generated multiple hypervectors for each, for instance, pixels in the image processing setting, we need to combine and contribute to class hypervector. For this, we will be using some simple logic operations, such as binding, bundling, permutation, based on specific application, kind of image processing or language processing. But in this work, we will be focusing on image processing. Let's first see how stream generators work. It is very similar like in stochastic and Unary computing. Like in stochastic computing, we may have a random stream generation by using a RNG, random number generator, at each clock cycle. Generate me a binary number, which is compared with S as scalar input to be represented in a bit stream. At each clock cycle, S as scalar value to be represented and R as the RNG output are compared in terms of if S is greater than R. If this is the case, the output returns me a 1. Otherwise, it's 0. After D clock cycle, in terms of this total dimension of a stream, I have my randomly generated vector. As a recall, in Unary computing setting, as proposed before, I used, instead of RNG, the Unary up counter generator, which is just simple binary counter starting from 0. At each clock cycle, the counter starting from 0 increase to 1, 2, 3, and going so on, be compared with the scalar input. It starts checking with if S as scalar to be represented in unary bit stream, if greater than this counter output or not. If it is, I record as 1 at my output bit stream, unary bit stream. In this way, I just guarantee that all those ones coming together until a point, and after counter beats the value of S, then the remaining becomes 0. Because in unary setting, we have aligned ones and zeros onto left or right, and in this way we just create a unary stream. Unary streams are advantages in terms of the toggling, because in random case we have many time going up and down in terms of the switching between 0 and 1, but in unary stream it's only one time, because all those ones come together and then zeros occur afterwards. So this way we have more energy efficiencies in compared to random setting. Speaking of randomness, which we will exploit, we can also have, instead of pseudo-randomness, quasi-randomness, which is a very well-known setting in stochastic computing. Here we see two examples of pseudo-randomness in pink and quasi-randomness in blue. By having two different sequences generated separately, if we scatter them, we can see visually what is the difference between this pseudo and the quasi setting. In quasi-randomness, we have a recurrent property, and we have more structure distribution of those sequences when we plot them. And if we have their distribution in terms of probabilities, we have more non-uniform distribution in the pseudo-randomness. But when we check the low discrepancy quasi-random sequences on the right-hand side, we have a more uniform distribution. This is important because similar to stochastic computing, which requires some strong orthogonalities, we have the same setting here, because especially for this symbol representations in hypervectors, we need them to be orthogonals. Especially for using quasi-randomness brings us, as you can see in the third line, as an orthogonality. When we plot their orthogonality by using any orthogonality metric, if we plot this, we see more smooth regions in terms of this any two vectors compared with orthogonality metric. This is important because during the learning phase, we need to create some unbiased vectors which are not similar to each other, that represent best different items such as symbols. We may have n different symbols, and those n different symbols maybe need to fully orthogonal. For image processing setting, I have positions and their corresponding intensities, as those are positions pixels. So for symbolic position representations, I need fully orthogonal, which means kind of each vector, each hypervector, having 0.5 probability internally, like equal numbers of plus and minus ones. But from 1 to n, each of them are fully orthogonal, should be. Beyond this, we will also need the numerical representations of each pixel value that I will also show. But first, for this fully orthogonalities, we may have two settings. One is pseudo-randomness and the other is quasi-randomness. And for the first, we may have something like LFSR, linear feedback shift registers, but for each symbol, I may need to have multiple of LFSR for each symbol. As you can see here, I may need to have n different LFSR settings, which is costly in terms of hardware, but for our proposal, we can have some unique architecture on the right-hand side, getting benefit from quasi-randomness, and only by using a single source that we propose in this work can be used to obtain n different orthogonal vectors from a single source. Our proposed solution will be using a quasi-random setting. In this, we will be using Van der Carpet sequences. As a reminder, van der Karpet sequences using some an hardwiring and changing the most to least significant bit and vice versa by making a simplistic hardwiring and can give us, which is called a base 2 VDC van der Karpet sequences. There are some other alternatives, but in this work we're just using this simple hardwiring most to least significant conversion. After generating this most least significant conversion, then by using the comparator, we have d different types of generations, and we can generate n different symbols. For this one, we propose at the output of this comparator as a regular setting, we use the T flip-flops, which has this shifted and the regular version be XORed, which guarantee that we can have many different types of orthogonal vectors from the output of the comparator, which are having 0.5 probabilities as the requirement of the orthogonality, but each have this high quality orthogonality. With this one, we just use a single source and multiple different versions of the vectors in our n different requirement for the symbols. This was for the position, but also we need to generate for the level hypervectors, which are the pixel values. On the right-hand side, in the regular setting, we have a random flipping approach. For different pixel values from 0 to 255, speaking of grayscales, we start with flow of -1s and then we need to target a flow 1s. So for this one, we just flip randomly, so the closer values will be having a similar, but the distant values having a very different distributions. So by this way, the learning mechanism keep understanding of the closer and different values. What we propose in this work, we will use this representation in terms of the unary-based level hypervector generation. By using a similar structure, we have a counter and a comparator for any value. Here we are optimizing it with left shifters of each different pixel value. And in this case, we have the closer pixels having the closer alignment of the ones, but for the distant values, there will be higher differences. For this, for example, having a pixel value of 75, we will have some ones come together and the remaining are 0. But when the pixel becomes a 76, let's say only one bit is changing, and then we will have a one more one of this group of ones and the remainings are 0. By this way, we keep track of closer values. This is the end-to-end design for the position hypervectors and the unary level hypervectors by using deterministic and unary encoding together. After we obtain our P as the position and L as the level hypervectors, we will just bind them by using XORs, and then we add them up by contributing to each class hypervector in the associative memory. Here are the results for this position hypervector generation compared to baseline design and our proposed quasi-random based deterministic design. The power consumption reduction is guaranteed by 98%, and energy efficiency improvement is by 15%. When we look at the level hypervector generation cost, when we use the unary computing, we improve power consumption until 68 times in terms of the reduction, and also we have area delay improvement up to 39 times. When we check the accuracy results, we use MNIST dataset in the medical setting, the medical MNIST dataset. For this, we have different results of subsets, but for example, for derma MNIST, we can improve the baseline HTC results in our proposal. For instance, the accuracy is 68 compared to the baseline of 62% of classification accuracy. All the other subsets can be found in the manuscript. Overall, we have incorporated a single source, streamlined and efficient position vector generation, and also by using a unary computing, we have a new proposal for level hypervector generation in hyperdimensional computing. This brings us a significant power consumption, energy efficiency, and area delay product improvements by a medical MNIST case study with the good accuracy scores. Thank you very much for your listening.